Okay, thank you very much for your patience. I apologise for the slight delay in starting this press conference this morning, or afternoon even. We had a special guest in one of our other sessions and it rather overran, and two of our speakers were in that session, so I'm afraid we are late starting. Nevertheless, I think we have a very exciting and interesting lineup to start off with our press conference programme here at EPSC. I hope that some of you will have been following the live stream, which is also going on during the duration of the meeting, courtesy of LMT. We're grateful to them for their support. We have three speakers today. Our topic overall is pushing the boundaries of planetary exploration. So we're going to start off with talking about asteroid mining. We're going to move on to talking about how we can get much more information through large samples of asteroids. And then we'll finally go to our final speaker, who will be talking about exoplanets, so planets orbiting other stars in our galaxy. Our speakers today are Galache from Aten Engineering. We have Pekka Janhunen from the Finnish Meteorological Institute, and we have Angelos Tsigaris from University College London. I'm going to hand over to JL in just a moment. I would just say, if you are watching this remotely via the Ustream, you are very welcome to ask questions. We will ask each of our speakers to talk, and then we will take questions from the floor for everybody to try and make up a little bit of time. So JL will talk, then Pekka, then Angelos, and then we will take questions both from journalists here in the room and from those watching remotely. So thank you very much for coming along to EPSC to watch or attend this press briefing. And JL, over to you.
Thank you very much. So I'll be talking about the SMA 2016 white paper that we presented. It's the brainchild of Amara Grabs, who's my co-author here, and we had 30 other international co-authors. First of all, SMA is what I call a loose acronym. It stands for Asteroid Science Intersections Within Space, Mine Engineering. And this is a workshop that took place in Luxembourg in September of last year. And we thank Europlanet, Luxembourg Ministry of the Economy, and ESA for their support. And you can see the participants there. So we got together the three asteroid mining companies who we had requested questions from, science questions. They sent us 35 questions in all. We had a few dozen scientists that were going to be answering that questions, or at least we would attempt that, some engineers, and we also had some policy people, business and finance people attending. And what distilled from this workshop was the finding of 6 science knowledge gaps that the asteroid mining companies needed to fill in order to be able to fulfill their mission of mining the asteroids. And I will step through these gaps. First of all, mapping asteroid spectra to meteorite spectra. So we take spectra of asteroids in space. We can also take spectra of meteorites here in laboratories, but we have great difficulty matching one to the other. And meteorites are asteroids that have fallen to Earth. So we need to be able to better understand what asteroids are made out of by matching these two spectra. Now, we also need, in order to take these spectra of asteroids, we need dedicated equipment for that. And all these are NASA-funded telescopes that discover asteroids and follow them on to improve their orbits, but they do not provide spectra or light curves or other type of characterization that is useful for, or will be required for asteroid mining. So we need dedicated equipment. We need to understand the regolith dynamics in microgravity, and especially on the space mining operations. Regolith is the fine dust that collects on the moon and on asteroids. And you can see here asteroid Itokawa on the left, the arrow points downhill. And we see that the fine grains of regolith all move downhill. And then if we look here at the image of this astronaut, who is Jack Schmidt, the only geologist to ever go to the moon, and you can see that his trouser legs are covered in dust, and that's one thing that they realized, that lunar dust is electrostatically charged, so the same way that your hair might stick to a balloon when you rub it, that's how dust sticks to materials. And we need to understand all this if we're going to be sending probes that are going to land on an asteroid and are going to be interacting with it, mining it, crushing rocks. And if you imagine, if you have gears in these probes, getting them full of dust that sticks to them electrostatically isn't going to be good. So we need to know how to deal with that. But of course we need to understand know which asteroids we need to go and mine. And ideally we'd like to find dark asteroids because they are the types that contain most water, that they're easy to get to, and that they fly by often. So ideally we'd have a very large catalog of mineable asteroids, such that if you're a mining company and you have a launch window, no matter when that launch window is, there will be an asteroid that's flying by that's useful to you to mine and that you can travel to. And going back to what asteroids are made out of, this is a very simple diagram on the left of the abundance of different types of asteroids by composition and by number in the asteroid belt and a bit further on. And near-Earth asteroids come from the asteroid belt. Over the course of millions of years, they are slowly pushed from the asteroid belt into near-Earth space. So if we could tell where a near-Earth asteroid came from in the main belt, we could quantify to some extent what its composition could be, and that is useful for asteroid mining. Even it's better to have, say, a 20% certainty that an asteroid is of a particular composition than to not know anything at all. And lastly, we need to improve the regolith simulants. So in order to test equipment, be that mining equipment or even spectroscopic equipment, etc., we need to have simulants of this regolith. And on the left is one such sample. And we believe that asteroids look something like what's there on the right. That'd be the structure. So you have very fine regolith on the outside, and as you go deeper, the regolith becomes coarser and you have bigger boulders. But we don't necessarily know that, and we would like to know not just what the surface regolith looks like, the dust that you can see here in this image, but underneath, what is the structure and the composition, because if you're going to be mining, you're not just going to be mining the top 1 to a few centimeters, you're going to want to go deeper inside. So a thank you to the 31 other people apart from me who participated in writing this white paper. Some people were there present in Luxembourg, other people did it online because we had the questions open in a public document. So thank you to all the people who gave up their time for this. And the white paper is available there if you want more information. Thank you.
Okay, good afternoon. So the topic of my presentation was asteroid touring nanosatellite fleet with single tether e-sails. And this concept is based on something called Coulomb drag propulsion, which is a way to harness natural space plasma flow for propulsive purposes of a spacecraft. It has two application domains, so if one applies it in the interplanetary solar wind, then we get the so-called electric sail or e-sail. If we apply it in low Earth orbit, then we get so-called plasma brake that can be used for satellite deorbiting, which is also important application to fight the space debris. And the reason why this is interesting is that it's kind of very efficient. I mean, if one measures efficiency by the lifetime integrated impulse divided by the propulsion system mass. And here is the concept how it looks like. So we have a small satellite, a small spacecraft, and then quite long tether, very thin tether, 10 to 20 kilometers long. There is some mass at the end, also contains some functionality. We call it the remote unit. Then we rotate it to keep it stretched, and this tether, if it's charged, it gathers thrust from the solar wind, and with so much thrust that we can achieve about 1 millimeter per second squared acceleration due to this solar wind force at 1 AU distance. And then one point about this arrangement is that it's possible to do pointing of the spacecraft. So one end of the spacecraft can have a telescope, and then we can turn the spacecraft in 2 angles by using just momentum wheels, so that the telescope will see the asteroid that we are making a flyby of. And then we made a proposal of this concept to ESA. ESA's call for new science ideas last year, and then it was kind of selected this year. Selected in the sense that ESA will look further into it, and actually this process has already started. And we can apply this idea in a variety of scales, but for example, we could have, if we use a dedicated launch vehicle, then we could have 50 nanosatellites flying through the asteroid belt. Each of them makes 6 or 7 flybys, so we get altogether about 300 or more asteroid flybys. The whole mission would last a little bit more than 3 years. And then data gathered during the mission is returned at the end by making a final Earth flyby for each spacecraft. And this is to keep the operations costs down. So this is a low-cost mission concept, mission architecture, to make flyby study of a massive number of asteroids, a large number of asteroids. We can estimate that we are talking about few hundred thousand euro cost per asteroid imaged, which is an improvement of about 2 orders of magnitude relative to the state of the art. And this is enabled by the e-sail propulsion, in particular in this case the single tether e-sail.
Thank you all for coming today. As Anita mentioned, we will discuss about exoplanets, and in particular about exoplanetary characterization. Since the last 20 years, we have discovered more than 3,000 exoplanets. And from these results, we now know that the number of planets in our galaxy is similar to the number of stars. And consider that only in our galaxy there are hundreds of thousands of stars. And imagine what happens in the whole universe. So there are many, many planets. But now we need to know more about them. We need to know their basic characteristics. And how do we do this? In this work, we use the transiting method. A transit is when a planet is passing between its parent star and us. As you can see in this figure, this is the transit of Venus in front of the Sun. The black dot is Venus. And the same method can be applied to exoplanets, with the only difference that since the star is very far away, we cannot see the planetary disk. But we can still, if we focus on the planet and its disk, a part of the planetary, a part of the stellar light is filtered through the planetary atmosphere. This is the thin circle surrounding the planet, where you can see in this figure. And if we observe the light coming from this small ring, this is the atmosphere of the planet. And if we resolve it in different wavelengths, we can identify the footprint of different molecules present in the planetary atmosphere. Of course, this is not an easy task. To be able to detect these features, we need very precise data. And today, this can be achieved only from space-based facilities. In particular, in this work, we used data from the Hubble Space Telescope, which is orbiting around the Earth. And it provided us with the best possible data today. However, until today, only single planets have been studied, or small numbers of planets. But a large number is important. And why is that important? Because large number of planets means better results, means that we can understand better the collective behavior of planets as celestial bodies without focusing on single cases. In our work, we studied 30 exoplanets and their atmospheres with the Hubble Space Telescope. And we found that for half of them, we couldn't detect anything. This, in practice, means that they are covered with clouds. For the rest of them, we could find an element that is very common even in our Earth, and this is water, of course in gaseous form. And this is because the planets we analyzed are gaseous giants like Jupiter and Neptune, and they are far different from rocky planets like the Earth. This picture tells us that there is huge diversity between exoplanets, but 30 is a small number. However, the future is bright, and with the launch of the James Webb Space Telescope next year, we will go from 30 to more than 100 atmospheres. And we hope in the next decade or so, dedicated missions like those on the right-hand side, smaller than the James Webb Space Telescope, will provide us with thousands of new spectra. But why do we need thousands? We need thousands because only with such large sample we will be able to answer the fundamental questions of planetary characterization today. These are: what are the exoplanets made of? What is the weather like there? Why are they so diverse? Why do we find so many different planets? And of course, the ultimate question: what are these planets habitable? Of course, we acknowledge that the 30 planets studied in this work is not sufficient to answer today all these questions in detail. However, today we can make a great step forward towards answering these questions, and in the future, hopefully, we will be able to understand more about worlds beyond the Earth. Thank you.
Okay, thank you very much to our speakers. Do we have any questions? Can I ask you to speak into the microphone and introduce yourself?
Okay. Hello, my name is Raivis Vilunds from daily newspaper Diena, and I wanted to ask a general question about asteroid mining. What are we looking for on the asteroids? What does humanity want to gain from them? What elements or compounds?
Mm-hmm. I think that ultimately we want everything that an asteroid can provide. We will find uses for it, but initially the first viable product, commercially viable product, I believe will be water. Water can be used, has a lot of uses. It can be drunk, obviously, but you can break it up to make oxygen and hydrogen. You can use hydrogen to produce rocket fuel. You can use it as radiation shielding as well. And the first uses, I believe, will be in low Earth orbit for water. You can have water for example, space tourism. There are people planning space hotels. And there are also people thinking about how to refuel satellites. So that's what I believe is going to be the first product.
Further questions? Tilina, do we have any on Twitter or online? Yes. Okay. Yeah. Sorry.
Why should we focus on asteroid mining if we know so few about them? Why not focus on moon base instead?
Well, I don't think it has to be a question of either or. Initially, my company is focused on asteroid mining because we believe that that's going to be the first step towards space resource utilization. But there are plenty of plans for resources to be used on the moon. Personally, I think that maybe the political situation in the moon might be a little bit harder than it is for asteroids. But I think that in the future, decades from now, we will be mining asteroids, the moon, and probably other planets and other moons.
There's a follow-up question. I mean, okay, it says this sounds like science fiction. And are you actually trying to make science fiction a reality?
Yes, and every bold idea, every reality that we have today was once science fiction, right? You're reading the tweet from a mobile phone, which 20 years ago, it was science fiction that you could have such a small, such powerful computer that connects you to the entire world in your hand. So yes, it is science fiction, but it will eventually become science fact.
Do we have any more questions from people attending? Just one moment. Yes? Luca.
Hi, Luca Maltagliati, Nature Astronomy. I have a question for the e-sails. Are there any plans to apply the same kind of system to the outer solar system exploration, like Uranus, Neptune, and so on, or even the Kuiper belt? I don't know.
Yes, indeed. I mean, this is a generic propulsion technology, so you can use it for almost any propulsive task in the solar system. The only limitation is that one cannot apply it for lifting satellite orbits, because our satellites are orbiting inside Earth's magnetosphere, where there is no solar wind. But everywhere else in the solar system, it's possible to apply this technology. And NASA is, in particular, NASA Marshall Space Flight Center is looking to, is analyzing in their own project to apply this technology to flying a probe at high speed out of the heliosphere. I mean, at much higher speed than Voyager and Pioneer did.
Nat, I think you had a question.
About the exoplanet talk, you mentioned about hot Jupiters, which is like gaseous planets, not like the Earth. How easy or common will it be to find or identify the Earth-like atmospheres and water, for example, on them?
Okay, so Earth-like planets are much smaller than gaseous planets, and hence their atmospheres are much smaller. So it is way more difficult to detect any kind of molecules on them. But more recent studies are focusing on exoplanets around smaller stars. So, for example, the TRAPPIST planets. And in this case, it becomes a bit easier. Of course, even with the James Webb Space Telescope, it will be also very difficult. But we are at the edge. In the future, something better than in this case, like James Webb, and again focusing on planets around small stars maybe give us some indications. However, planets around M dwarfs are different from planets around Sun-like stars, but this is our best chance right now.
Okay, I think we have some more questions from people watching remotely.
There's a question asking if there's any policies implemented already for mining asteroids and other objects, because once it starts, there might be companies competing to try to get the resources.
Yes, that will probably happen. Right now, we have the 2015 Space Act in the US, which says that private companies that go to an asteroid and extract material from it will own that material and can profit from it. And just this year, in August, the government of Luxembourg enacted a similar law. So that's 2 countries now, but both of them understand that this needs to be international, that other countries need to follow suit so that there can be an international agreement. And right now, you can't own an asteroid and you can't reserve mining rights on an asteroid. And probably there has to be some policy instituted on that so that you don't have, like you say, 2 mining companies or 3 going to the same asteroid and you get, I guess, you'd get a little fight or whatever.
Do we have any more questions from people here in the room? I don't think so. Talina, any more remote ones?
I have a question for Pekka. Can I ask?
Okay, yes, of course.
Yes. How heavy can you move an object with the sail?
The answer depends on whether we talk about single tether e-sail or multi-tether e-sail. So if we use a single tether e-sail, and if we want to go to the main belt at one go, so making only one revolution around the Sun, then we need 1.0 millimeter per second squared acceleration at 1 AU, and then the flying mass of the package must be approximately 5 kilograms at most.
Okay.
But if we could consider a near-Earth object version of the mission, where if there is no need to go to the main belt, but if it's enough to go to make flybys of near-Earth objects, then we could increase this to about 10 kilograms roughly.
Okay. So it's not going to be applicable for crude capsules, say? Because then we're talking about...
No, well, I mean, this multi-tether e-sail could perhaps achieve about 1 Newton thrust altogether. I mean, that seems to be some kind of practical maximum. If one improves the tether technology, so if one makes some fancy carbon nanotube tethers or something like that, which currently is science fiction, then maybe in the future, maybe it's not even out of question to even move manned capsules, but that's like behind many doors which must first be opened. But of course the main application of this e-sail to help manned exploration would be through asteroid mining. So we could fetch water from asteroids using this e-sail as logistics service, and then you can apply that rocket propellant made out of that water for bidirectional manned traffic to Mars, for example. So this is the vision that we had already some years ago and published it in Acta Astronautica. I think 3 years ago. So I'm very much on the same page with you regarding the use of water from asteroids, and we think that by using the e-sail we could ease up the task by lifting the delta, by making it easier to achieve a higher delta V than what is possible with traditional technologies.
Good.
Okay. Any last questions that have come through? No. Okay. Well, in that case, thank you very much for coming. We are very grateful for your presence here. I encourage you to look at the live stream of the sessions that are going on today, tomorrow, for the rest of the week. We have another press briefing here on Thursday. It will be also at 1 o'clock, hopefully starting on time next time. And that will be with members of the Cassini team talking about the Cassini mission end, which there has been a great deal about lately. And there will also be 3 panel members talking about the encounter of comet Siding Spring with Mars and what we found from that. So please do join us again on Ustream for that briefing. Come here. Please attend in person if you can, or follow us on Twitter or on live stream. Thank you very much.